sleepy story facts and to a gentle little sleep story made of quiet truths from our solar system. The kind that can sound imaginary at first, until you remember how wonderfully strange space can be. So settle in now. Let your shoulders soften. Let your breathing slow down, easy and unforced. And as you get comfortable, you can let this nighttime story carry you, thought by thought, toward deep sleep. Tonight, we're drifting to a place that isn't a planet and isn't a star, but a calm in-between point in space where careful machines can hover and watch. Between Earth and the Sun, about 1.5 million km away from us, there's a special region called Lagrange point lone. It's often described as a balance point, not because gravity disappears, but because the push and pull of the system can be arranged in a way that lets a spacecraft stay aligned with Earth as both travel around the Sun. In that peaceful corridor, the Sun's gravity pulls one way. Earth's gravity adds its own gentle tug, and the spacecraft's orbital motion contributes what feels like a steady outward tendency. Together, these effects create a helpful sweet spot where a satellite can keep its position with only small, occasional adjustments, saving precious fuel over long missions. That steady alignment is the real gift of lone. From there, a spacecraft can keep an uninterrupted view without Earth repeatedly blocking the scene. For solar watching missions, it's like having a permanent seat facing the Sun all day and all night, while still staying close enough to send information home. One famous resident of this region is SOHO, the Solar and Heliospheric Observatory. From its post near Lone, SOHO keeps a continuous watch on the Sun's surface and outer atmosphere, tracking changes that can lead to solar flares and huge eruptions called coronal mass ejections. Another spacecraft, DSCOVR, also works from near Lone. It helps monitor space weather and also measures how energy moves through Earth's system, quiet numbers and subtle shifts that tell scientists how our planet interacts with sunlight. Even though L1 is sometimes spoken of as if it's a motionless parking spot, spacecraft don't truly freeze there. Many travel in looping paths known as halo orbits, circling around the region in a slow, controlled pattern. That graceful motion helps them stay stable, avoid drifting, and keep their instruments pointed the right way. And Lone isn't alone. It's one of 5 Lagrange points in the Earth-Sun system, places where gravity and orbital motion combine in useful ways. Another well-known region is Eltwo, on the far side of Earth, away from the Sun. That's where the James Webb Space Telescope operates nearby, with the Sun and Earth largely in the same direction, so its delicate instruments can stay shaded while it gazes into deep space. But L1 remains the classic lookout for watching the Sun directly, and it's especially valuable for early warnings. If a burst of charged particles heads our way, monitors near L1 can detect it before it reaches Earth, sometimes giving 15 to 60 minutes of notice. That small window can help protect satellites, astronauts, and even sensitive power systems on the ground. The idea of these points goes back to the 18th century, when mathematician Joseph Louis Lagrange described how 2 large bodies can create stable regions for a smaller one. Today, those quiet coordinates guide mission, planners the way lighthouses guide ships, steady, reliable, and surprisingly serene. And as you listen to this relaxing story of space, you can imagine those patient spacecraft floating in the sun's glow, keeping watch. While you do the opposite, you let your eyes rest, you let the day slip away, and you begin to fall asleep. As we continue this relaxing nighttime story, we drift away from that quiet balance point in space and float inward toward a planet hidden behind pale clouds, warm and distant in the dark. Venus has one of the strangest time tricks in the solar system. On Venus, a single day can last longer than an entire year. Here on Earth, we're used to a simple rhythm: one spin for a day, one trip around the sun for a year. But Venus turns with an almost dreamy slowness. It needs about 243 Earth days to rotate once on its axis. Yet, it completes its orbit around the sun in only about 225 Earth days. So while Venus is still finishing one slow turn, it has already gone all the way around the sun. And Venus adds one more twist. It rotates the wrong way compared with most planets, in what scientists call retrograde rotation. If you could stand on its surface, just as a calm imagination exercise, ignoring the truly harsh reality there, the sun would seem to rise in the west and set in the east, because Venus is moving along its orbit while it slowly spins. There are two useful ways to describe a day. The sidereal day is the pure rotation time, those 243 Earth days, but the solar day, meaning sunrise to sunrise, is shorter, about 117 Earth days. Even the shorter version is still so long that the sunlight would linger and linger, as if the planet is taking its time on purpose. This slow spin shapes the planet's atmosphere and weather. With such gentle rotation, Venus doesn't develop the same kind of strong Coriolis-driven patterns that steer storms on Earth. Near the surface, winds can be sluggish, while higher up the atmosphere races around the planet far faster. An eerie contrast between slow ground time and swift sky motion. Venus is also unbelievably hot, with surface temperatures around 460 C. It's even hotter than Mercury, despite being farther from the sun. The reason is a powerful greenhouse effect. A thick atmosphere traps heat so efficiently that the planet can't cool down the way we might expect. And because the day-night cycle is so stretched out, and the clouds are so dense, temperatures stay surprisingly even across the surface for a long time. Astronomers couldn't easily measure Venus's rotation because its bright cloud cover hides the ground. In the 20th century, radar observations and spacecraft data finally revealed the truth. Venus really does turn, just extremely slowly and backward. Why is it like this? Scientists have ideas, including long-term tidal effects between Venus and the sun that may have slowed and altered its spin over billions of years. The details are still studied, like a soft mystery that refuses to hurry. For missions, this strange timing matters. A lander would have to endure relentless heat for long stretches and operate under a day-night rhythm unlike anything on Earth. And in this gentle bedtime story about the solar system, Venus reminds us that normal is rare in space, and that it's safe tonight to let time slow down. Saturn could float in water in this quiet bedtime story, drifting through the solar system. We ease our way outward now to Saturn, the ringed giant that looks heavy and grand, yet holds a surprisingly gentle secret. In a simple, scientific sense, Saturn could float in water if you could imagine a bathtub big enough to hold a planet. The reason comes down to density, which is a calm way of asking, how much mass is tucked into a given volume? Saturn's average density is about 0.687 g/cm3. Water is 1 g/cm3. Because Saturn's average is lower than water's, the float idea actually works in theory. Of course, no ocean could ever hold Saturn, and Saturn wouldn't stay neatly shaped if you tried. But as a fact to carry into deep sleep, it's a lovely one. The huge planet is, on average, lighter than water. Saturn is made mostly of hydrogen and helium, very light elements. And because the planet is so enormous, that light material is spread across a vast volume. There is likely a denser core, rocky or icy, but it's only a small fraction of the whole. The rest is gas, gradually compressing into thicker, heavier layers the deeper you go. Even though Saturn is low density, it's still massive, around 95 Earth masses, so its gravity is nothing to dismiss. If you could stand on a solid platform at the level where Saturn's atmosphere is measured, you'd actually weigh a little more than on Earth. But Saturn doesn't offer a true surface to stand on, only cloud layers fading into deeper and denser material. That lightness also connects to Saturn's shape. The planet spins quickly, taking a little over 10.5 hours to rotate once. That fast spin makes Saturn bulge at the equator and flatten at the poles, giving it a noticeably squashed, oblate appearance, like a soft sphere gently pressed from above and below. And then there are the rings, bright, delicate bands of ice and rock. They don't add much to Saturn's mass, but they make it unforgettable. A planet that seems decorated for the night. Scientists pay attention to facts like density because they hint at how a world formed. Saturn's low density suggests it grew in the colder outer solar system, where light gases were abundant and could be gathered into a giant, airy globe. Compared with Saturn, the other giants are denser. Jupiter's stronger gravity compresses its interior more. Uranus and Neptune contain more ices and heavier compounds, raising their average densities, so Saturn becomes a soft reminder in this relaxing story. Size and heaviness aren't the same thing. Something can be immense and still, by the numbers, surprisingly light. Jupiter's colossal storms last for centuries as this gentle sleep story continues. We drift from Saturn's quiet lightness to Jupiter vast, banded, and softly glowing, like a lantern made of clouds. And there, in its atmosphere, time behaves strangely again, because some storms on Jupiter can last not just days or weeks, but centuries. The most famous is the Great Red Spot, a gigantic anticyclonic storm in Jupiter's southern hemisphere. Anticyclonic simply means its winds swirl opposite to the direction of a typical cyclone on Earth. It's so large that, at times, 2 to 3 Earths could could fit inside its oval boundary. People have been watching this storm for a very long time. Observations go back to at least the 1600s. Imagine that. While generations rose and fell on Earth, this one great whirl of wind kept turning in Jupiter's sky, steady and enduring. Its winds can race at over 400 km/h, far beyond the scale of ordinary weather at home. On Earth, storms weaken when they run into continents, mountains, and changing ocean temperatures. But Jupiter has no solid surface to break things apart. Instead, it offers endless atmosphere, layer upon layer, and a deep internal heat source that keeps energy flowing upward. The Great Red Spot also sits between strong jet streams. You can picture them as fast, invisible rivers of air that help hold the storm in place, discouraging it from wandering too far. That trapped position may be part of what helps it survive. In recent decades, the Great Red Spot has been shrinking, becoming smaller than it once was. Yet it remains active, and no one can say for sure whether it will slowly fade, transform into something new, or continue on quietly spinning far into the future. Beneath the cloud tops, the storm likely reaches much deeper than a storm on Earth ever could. The Juno spacecraft detected subtle gravity clues around the region, suggesting the Great Red Spot may extend down hundreds of kilometers into Jupiter's atmosphere. That depth makes it feel less like a surface storm and more like a great, slow engine inside the planet's weather. Jupiter's air is mostly hydrogen and helium, mixed with compounds such as ammonia and others that help create its bands and shifting colors. The planet's strong heat and rapid rotation, about a 10-hour day, drive powerful convection, jet streams, and long-lived vortices. Smaller storms can collide and merge, sometimes building larger systems that persist for years or far longer. Even the Great Red Spot's reddish color remains a gentle mystery. Some scientists suspect sunlight triggers chemical reactions, possibly involving sulfur or phosphorus-bearing compounds, creating that warm, rust-like tint across different cloud layers. Studying these storms helps researchers understand fluid motion on a colossal scale. And it also helps with exoplanets, many of which resemble Jupiter in size and composition. And now, as the storm continues its slow turning somewhere far away, you can let your own thoughts slow too, becoming softer, quieter, ready to fall asleep. Hyperion spins chaotically in our soft nighttime story. We're still in Saturn's neighborhood, where the rings glow faintly and the moons drift like quiet thoughts. And among those moons is Hyperion, an odd little world that doesn't spin in a calm, steady way. Hyperion is one of Saturn's more unusual moons, known for its irregular, spongy shape and its low density. Instead of being smoothly rounded like many larger moons, it looks lumpy and pitted, as if it were carved from porous ice, and then gently tapped by countless impacts. But the strangest part is its motion. Most moons eventually become tidally locked, turning so predictably that the same face points toward their planet. Hyperion doesn't do that. It tumbles. Its rotation is chaotic, meaning its spin axis wanders and flips in ways that can't be neatly predicted far ahead. As it orbits Saturn, its odd shape and gravitational interactions, especially its relationship with the much larger moon Titan, help keep it in this restless, rolling rotation that tumbling changes what day means there. On Hyperion, sunlight doesn't follow a familiar rhythm of regular mornings and evenings. Instead, light can fall across different regions in shifting patterns, as if the moon is slowly turning in its sleep, never settling into one comfortable position for long. Images and measurements from the Cassini mission helped confirm just how strange Hyperion is, showing a heavily cratered surface with deep, sharp-edged pits that contribute to its famous sponge-like appearance. Scientists value moons like this because they reveal how shape, orbit, and gravity can combine to create unexpectedly complex motion. Quiet reminders that the solar system still holds gentle mysteries. Pluto may hide subsurface oceans we're far from the sun now, at the quiet edge of the solar system, where even sunlight feels like a distant memory. And yet, in this calming bedtime story, Pluto offers a surprising possibility. Beneath its frozen surface, it may still be holding on to liquid water. Pluto is intensely cold at the surface, often described as around -230 C, cold enough that most familiar things would be locked solid. For a long time, that distance and cold made the idea of liquid water seem almost impossible. But once New Horizons flew past Pluto, it revealed a world that looked unexpectedly active and textured, with regions that seemed young or renewed rather than ancient and unchanged. Those surface clues pushed scientists to ask a soft, intriguing question. Could something warmer be moving below? A major focus is Sputnik Planitia, the bright, heart-like basin filled with nitrogen ice. Some research argues that Sputnik Planitia's position and behavior make more sense if there's a denser layer beneath the ice shell, consistent with a subsurface ocean, helping create a mass anomaly that influenced Pluto's orientation over time. How could an ocean stay liquid so far out? One explanation is slow internal heating from radioactive decay inside Pluto's rocky interior, with thick layers of ice acting like a blanket that holds that warmth in. Another possibility is that the water may be mixed with substances that lower the freezing point, such as ammonia, making the ocean more resistant to freezing solid. No one has directly seen an ocean inside Pluto yet, and it remains an active area of research rather than a settled fact. Still, Pluto has joined the growing list of icy worlds where hidden oceans are considered plausible, expanding the idea that liquid water might exist in more places than once imagined. And that's a comforting thought for a nighttime story. Even at the fringes, even in the dark, warmth can linger quietly out of sight, held safely under layers of ice. Saturn's North Pole hexagon back in Saturn's calm, distant skies. Our bedtime story arrives at the planet's North Pole, where the clouds don't swirl in a simple circle, but settle into a shape that feels almost impossible, a giant, steady hexagon. This six-sided pattern is not a solid structure. It's a long-lived atmospheric feature, essentially a jet stream that wraps around the pole in a geometric loop. It was first noticed during the Voyager flybys in the early 1980s, and later observed in far more detail by the Cassini mission. The hexagon is enormous, about 30,000 kilometers across, so wide that it's often described as being roughly twice the width of Earth. Winds along the jet can be extremely fast, with reports of speeds up to around 500 kilometers per hour. Yet, the overall pattern remains remarkably stable. One reason it fascinates scientists is that it seems locked in place relative to Saturn's rotation, rather than drifting in longitude like many other cloud features. Cassini watched it for years, and it didn't simply fade away, which makes it feel less like ordinary weather and more like an enduring rhythm in Saturn's atmosphere. As for why a hexagon forms at all, the best explanations involve fluid dynamics, how fast-moving flows can organize into polygon shapes under certain rotating conditions. Similar polygon patterns have been recreated in laboratory experiments with rotating fluids, supporting the idea that Saturn's hexagon is a natural consequence of atmospheric motion, even if the full details of its size and persistence are still being studied. And right near the center, Saturn's North Pole also hosts a tight polar vortex, like a hurricane-shaped swirl nested inside this larger, quiet geometry. In the softness of this nighttime story, it's a lovely image to rest with, a giant planet breathing heat from within and drawing a perfect shape in clouds over and over. While you drift toward deep sleep, diamond rain on Uranus and Neptune. As this gentle nighttime story continues, we drift even farther out, past Saturn's soft geometry, toward Uranus and Neptune, where the light is dimmer, the cold is deeper, and the physics becomes almost dreamlike. There's a famous idea that on Uranus and Neptune, it can rain diamonds, not in the clouds you'd see from far away, but deep inside the planets, where pressure becomes overwhelming. These worlds contain methane and other carbon-bearing compounds, and under extreme pressure, that carbon may separate out and crystallize into tiny diamond structures. Recent lab work has supported the basic chemistry. When hydrocarbon materials are compressed and heated to ice giant-like conditions, carbon can form nanodiamonds. If that diamond formation happens inside Uranus and Neptune, the diamonds would be denser than the surrounding fluids, so they would tend to sink like slow, glittering rain, falling inward through layers of exotic ice and fluid. Deeper down, temperatures likely rise enough that the diamonds might melt or transform. So the process may not be a neat pile of gemstones, but part of a larger internal cycling of carbon and heat. Scientists are still working out how much this process could affect each planet's internal energy and structure, including whether it plays any role in their unusual magnetic fields. And because Uranus and Neptune have only been visited up close by Voyager 2 flybys, without an orbiter to map their interiors in detail, much of this remains informed inference rather than direct observation. In the language of a relaxing bedtime story, though, it's enough to picture it softly. Deep beneath blue-green clouds, far from the sun, carbon is being shaped by pressure into something perfectly crystalline, and then drifting downward slowly, quietly. As you fall asleep, Venus's atmosphere crushes landers within minutes, In this gentle bedtime story, we return to Venus, still wrapped in thick cloud, still glowing with trapped heat, where landing is less like touching down and more like enduring an ocean of air. Venus is famous for having crushing surface pressure, around 92 times Earth's, alongside extreme heat. That pressure alone is enough to destroy most unprotected hardware quickly, and the temperature near the ground is so high, often cited around 400 and 6,400 and 65 degrees C, that electronics and materials fail fast. It's one of the reasons Venus surface missions are rare, short, and incredibly difficult compared with orbiters or higher altitude concepts. Even so, a few landers did make it. The Soviet Venera missions in the 1970s and 1980s successfully returned data from the surface, but their lifetimes were measured in minutes to a couple of hours, not days. The longest-lasting Venus landers are often reported at roughly around 2 hours before the environment overwhelmed them. Venus also adds chemical stress. Its clouds contain sulfuric acid, meaning a spacecraft has to survive not only pressure and heat, but also corrosive chemistry during descent. And because the air is so dense, descent behavior changes too. Drag is strong, slowing a probe as it falls through the atmosphere before it finally meets the furnace-hot ground. In the calm tone of a nighttime story, Venus becomes a reminder that atmosphere can be as powerful as stone. On that world, the air is heavy enough to press and press until even strong machines must eventually rest. Titan has rivers, lakes, and rain of methane tonight. In this slow bedtime story, we return to Saturn once more and let our attention settle on Titan, its largest moon, quiet, orange-hazed, and strangely familiar in the way it shapes its landscapes. Titan has rivers, lakes, and even seas, but they aren't made of water. They're made mostly of liquid methane and ethane, because Titan is so cold that these hydrocarbons can flow the way water flows on Earth. So the rewritten section keeps the same ideas without leaning on precise numbers. On Titan, methane doesn't just sit on the ground. It cycles. It can evaporate from the surface, gather into clouds, and fall again as rain, creating a full methane weather system. In different seasons, storms can form in different regions, and the surface shows signs that liquid has recently moved darkened stretches, branching channels, and smooth areas that look like they've been rinsed clean. Many of Titan's lakes cluster near the poles, where conditions allow liquids to persist longer instead of quickly evaporating away. Some of these bodies are wide enough to feel like true seas in the imagination, broad, dark surfaces tucked into icy shorelines, with inlets and curved shores. One of the most famous is Kraken Mare, a vast sea of liquid hydrocarbons. It's so large that it changes how Titan feels as a world, not just a moon, but a place with coastlines, basins, and weather. And Titan's atmosphere helps all of this happen. It's thick, rich in nitrogen, and layered with a high orange haze made from complex organic chemistry. That haze hides the ground from ordinary cameras, which is why radar mapping has been so important for revealing Titan's surface shapes, rivers, valleys, dunes, and lake edges that would otherwise stay invisible. Even more quietly fascinating Titan may also hide another kind of ocean, one buried deep beneath its icy crust. If that subsurface ocean exists, it would likely be liquid water, possibly mixed with ammonia, resting far below the methane rains and shorelines. So Titan becomes a rare kind of world, one with active liquid on the surface, real weather above it, and perhaps another hidden sea far below, a layered, living landscape, moving slowly in the dark. Mercury is slowly shrinking in this calming nighttime story. We drift inward again, closer to the sun, and rest our attention on tiny Mercury, quiet, airless, and slowly changing shape over very long time. Mercury has been found to be gradually contracting as it cools, leaving behind wrinkled, cliff-like features on its surface that act like evidence of that shrinkage. As Mercury's interior loses heat, it can contract, and the crust responds by compressing and breaking into long, curved cliffs called lobate scarps, often described as giant stairsteps in the landscape. Because Mercury has no thick atmosphere or active weather to erase these landforms quickly, those scarps can remain visible for immense stretches of time. Observations from spacecraft imagery have also suggested that some of Mercury's fault scarps may be geologically young, which supports the idea that Mercury's contraction may still be continuing today. Researchers debate the exact amount of total shrinkage over Mercury's history, but multiple lines of work place it in the range of a few kilometers of radius change since formation. So, in the soft rhythm of a bedtime story, Mercury becomes a small, steady example of planetary aging, cooling quietly, tightening slowly, and leaving gentle wrinkles across a sunlit world. The moon is drifting away from Earth as this relaxing nighttime story continues. We come back home for a moment to the familiar moon, hanging quietly above Earth, doing something so slow and steady that it feels almost unreal. The moon is gradually moving farther away from Earth by about 3.8 centimeters per year. And this has been measured very precisely using laser ranging experiments with retroreflectors placed on the moon during the Apollo era. This gentle drifting happens because of tidal interactions. Earth's gravity pulls on the moon, and the moon's gravity pulls on Earth's oceans, raising tides. The friction involved transfers some of Earth's rotational energy to the moon's orbit, nudging the moon outward over time. As a result, Earth's rotation slows a little, meaning Earth's days lengthen very gradually across long timescales. This kind of tidal evolution isn't unique in space, but the Earth-Moon pair is especially noticeable because the moon is relatively large compared with its planet, making the exchange of energy and angular momentum more significant than in many other planet-moon systems. In the soft language of a bedtime story, it's a comforting thought. Even the moon is on a slow journey, drifting outward in near silence, so slowly you'll never feel it day to day, while you do the opposite, letting yourself drift inward toward rest, toward deep sleep. Jupiter's magnetic field influences its moons in this gentle nighttime story. We drift back to Jupiter again, so enormous, so steady, that even the space around it feels shaped and guided by its presence. One of Jupiter's strongest, invisible features is its magnetic field, which which creates a vast magnetosphere filled with charged particles. Jupiter's magnetic field is far stronger than Earth's, often described as about 20 times stronger at the cloud tops. And Jupiter's overall magnetic moment is vastly larger, helping it build an immense magnetic environment. That magnetosphere traps energetic particles and forms intense radiation belts, which is one reason spacecraft operating near Jupiter must be designed to handle harsh radiation conditions. This magnetic environment doesn't stop at the planet. It reaches outward into the region where Jupiter's major moons orbit, influencing them in different ways. Io, for example, moves through Jupiter's magnetic field and plasma environment, and this interaction helps drive electrical currents and auroral effects connected to Jupiter's poles. Some moons may also generate their own magnetic signatures within Jupiter's field. Ganymede is especially notable because it has its own intrinsic magnetic field, creating a complex interaction zone where Jupiter's field and Ganymede's field meet. And for ocean worlds like Europa, magnetic measurements have been used as part of the broader evidence that a conductive layer consistent with a salty subsurface ocean may exist beneath the ice. So Jupiter isn't just a planet with moons orbiting it. It's more like a vast, humming system where magnetism quietly connects worlds through invisible threads. While here at bedtime, everything can feel slower, softer, and ready to fall asleep. Triton orbits Neptune in the opposite direction. In this quiet nighttime story, we drift out to Neptune's dark blue distance, where the sunlight is faint, and everything moves a little more slowly. And there, Triton stands out as a moon that seems to travel the wrong way, like a thought gently drifting against the current. Triton is Neptune's largest moon, and it orbits in a retrograde direction, meaning it goes around Neptune opposite to the direction Neptune spins. This is extremely unusual for a large moon, and it's one of the strongest clues that Triton likely did not form alongside Neptune in the same rotating disk of material. No citation available this turn. Instead, the leading idea is that Triton was captured by Neptune's gravity long ago, possibly after a close encounter involving a binary object where one body was flung away and Triton was left behind in orbit. Over time, tidal interactions would have helped reshape that captured orbit into something more circular while keeping its backward direction. No citation available this turn. That backward orbit also has consequences because Triton moves against Neptune's rotation. Tides act in a way that slowly drains orbital energy, which can make Triton spiral inward over very long timescales. In the distant future, that inward drift could bring Triton close enough to be torn apart, potentially feeding material into a ring system. No citation available this turn. And yet, Triton is not just a captured path, it's a living-looking world. Voyager 2 images showed an icy surface with signs of activity, including plume-like geysers and young terrain that suggests resurfacing despite the intense cold. The asteroid belt is mostly empty space in this calming nighttime story. We drift into the space between Mars and Jupiter, to a place that movies often show as crowded and dangerous. Even though the real asteroid belt is mostly quiet, wide open space, spacecraft have crossed it many times without needing to dodge constant rocks, because the asteroids are spread very far apart. Even though there are many asteroids, the belt's total material is surprisingly small compared with what people imagine. One helpful way to picture it is this. If you were standing on a random asteroid, you likely wouldn't see another one nearby, just dark space and distant sunlight. A few large bodies carry much of the belt's identity, including Ceres, about 950 km across, along with Vesta, Pallas, and Hygiea, while most other asteroids are far smaller fragments. The belt's combined mass is only a small fraction of the Moon's mass, which is another reason the region isn't packed like a debris field. The asteroid belt also isn't the remains of a destroyed planet in the usual scientific explanation. Instead, it's widely described as leftover building material that never became a planet, in part because Jupiter's gravity stirred up the region and made growth by gentle merging much harder. And in a relaxing bedtime story, that emptiness becomes soothing, not a chaotic minefield, but a broad, silent lane of scattered stones where you could drift for a long time, seeing almost nothing at all while you fall asleep. A failed planet zone between Mars and Jupiter. In this calm nighttime story, we return to the wide lane between Mars and Jupiter, a place that sounds crowded in imagination, yet is mostly quiet and spread out. This region is the asteroid belt, and it's sometimes described as a failed planet zone, meaning a planet never fully formed there. One classic explanation is that Jupiter's strong gravity stirred the area early on, disrupting gentle growth and making collisions more destructive than constructive. Over time, instead of gathering into one world, much of the material stayed fragmented, leaving behind countless small bodies rather than a single planet. It's also important that the belt doesn't contain nearly enough mass to be the remains of one full-sized planet, which is why modern explanations usually favor interrupted or prevented formation rather than a single destroyed world. Older lost planet ideas, sometimes linked to a hypothetical planet called Phaeton, exist mostly as historical speculation rather than the mainstream scientific view today. And yet, the belt still holds clues. Different asteroid types and asteroid families hint at a complicated history of heating, collisions, and reshaping, like a quiet museum of unfinished beginnings. In the soft tone of a bedtime story, it becomes a gentle thought, a place where a planet might have been, and where the solar system chose a different, calmer pattern instead. Uranus's moon's orbit in a tilted plane in this relaxing nighttime story. We drift out to Uranus, the planet that seems to roll along its path, turned almost onto its side. Uranus has an extreme axial tilt, often given as about 98 degrees, meaning its spin axis lies nearly in the plane of its orbit. Because Uranus is tipped, its main moon's orbit in the same sideways equatorial plane, following the orientation of Uranus's equator rather than the solar system's usual flat disk. This makes the Uranian system feel uniquely rotated compared with most other planets and their moons. That extreme tilt is still not fully explained with certainty, but a widely discussed idea is that a major early event, such as a giant impact or impacts, could have tipped Uranus over while its system was forming. With the planet rotated, the moons and rings we see today appear aligned to that new tilted equator, as if the whole system learned a new down direction. This sideways setup also creates unusual seasons across Uranus's long year. Each pole can experience long stretches of sunlight, followed by long stretches of darkness. In the soft rhythm of a bedtime story, it's a peaceful image, small icy moons circling a tilted giant, moving through decades-long patterns of light and night, slow enough to lull any busy mind toward deep sleep. The solar system orbits the Milky Way in this gentle nighttime story. We zoom out from planets and moons and rest our attention on something even quieter. The solar system itself is always traveling, slowly circling the center of the Milky Way. I can't pull fresh sources in this moment, but the rewrite keeps your same core facts and pacing. This journey is sometimes called a galactic year, one full orbit around our galaxy, and it takes roughly 225 to 250 million years. Imagine that length of time like a long, slow breath the galaxy takes, while our sun and all its planets move along with it. Even though the motion is fast by human standards, the Milky Way is so enormous that the trip still takes hundreds of millions of years. Our path isn't a perfect circle either. It's a gentle, stretched curve, and the solar system also bobs slightly above and below the galaxy's main disk as it goes, like a quiet boat rising and falling on an invisible tide. Sometimes people wonder if that up and down motion could connect to patterns in Earth's history, like cycles of change or extinctions. It's an interesting idea, but the evidence is still uncertain, and the galaxy keeps its secrets carefully. What holds us in orbit is gravity, not just from the bright stars we can see, but from the Milky Way's total mass, including matter we don't see directly. Altogether, it shapes the spiral arms, the star paths, and the calm, steady routes that solar systems follow. And through this long orbit, the night sky itself slowly changes. Constellations are not permanent pictures. Over deep time, nearby stars shift, and our viewpoint drifts, and the familiar patterns rearrange like slow-moving sand. Yet even with all that motion, space remains vast. Close passes between stars are rare. Most of the time, our solar system simply glides onward, quietly, with plenty of room. So if this bedtime story feels wide and spacious, it's because it is. You are resting on a world that's traveling with its star, and its planets, and its distant icy clouds, all of it moving together through the Milky Way, on a journey so slow you never feel it, perfect for a calming narration as you fall asleep. Series shows bright salt patches in this relaxing nighttime story. We drift back into the wide, quiet space between Mars and Jupiter to Ceres, a small world that looks calm from afar, yet holds bright marks that shine like pale footprints in dust. Ceres is the largest object in the asteroid belt and is classified as a dwarf planet, and spacecraft images revealed striking bright areas on its surface. I don't have access to my usual verification tools in this moment, so I'm keeping the rewrite faithful to your original ideas without adding extra precise numbers. The most famous bright patches sit inside a crater, where a central region appears especially luminous, like someone sprinkled a fine white powder across dark ground. Scientists interpret this brightness as salt-rich material left behind after salty liquid or brine reached the surface and then lost its water, leaving reflective deposits behind. It's a gentle, familiar process in an alien setting. On Earth, when a shallow lake dries, pale minerals remain. On Ceres, the same basic idea may happen far from the sun. Briny material rises, spreads, and then the volatiles fade away, while salts stay. This is part of what made the Dawn mission's visit to Ceres so surprising. Ceres didn't look like a completely dead leftover rock. Those bright areas suggest recent activity by asteroid belt standards, signs that internal warmth, impacts, and cracks may still help material move upward from below, and that possibility changes the feeling of the asteroid belt. It's not only a failed planet zone of scattered stones. It also contains at least one body with a subtle inner story, quiet chemistry, slow motion, and bright salt shining softly in the dark. Moons outnumber planets, and some are geologically active in this soothing nighttime story. We pull back and look at the solar system as a whole and notice something quietly astonishing. Planets are the headline, but moons are the crowd. Notes that, as of March 25, 2025, there were 891 confirmed moons in our solar system. Counting moons of planets, dwarf planets, asteroids, and trans-Neptunian objects. Even if you only focus on moons around the major planets, the numbers are still huge. This kid-friendly solar system guide lists Saturn with 274 moons, and Jupiter with 95 known moons as of March 2025, showing how easily moons can outnumber planets. And as discoveries continue, those counts can change, which is part of what makes the outer solar system feel so alive and unfinished. But the most surprising part isn't only how many moons exist, it's what some of them do. A few moons are geologically active, meaning they aren't just silent rocks in orbit. Io is famous for intense volcanism driven by tidal forces, and worlds like Europa and Enceladus are studied for signs of subsurface oceans and internal heat that can keep ice moving and surfaces renewing. Titan adds a different kind of activity, with a thick atmosphere and surface liquid cycles that reshape its landscape over time. So, in the calm tone of a bedtime story, it's comforting to remember the solar system isn't only 8 planets moving in silence. It's a much larger family of moons, some quiet, some restless, each circling patiently in the dark. While you let your own thoughts slow, soften, and drift toward deep sleep, Earth shares its orbit with Trojan asteroids in this calming sleep story. We stay close to home, but notice something quietly surprising. Earth may have small companions that share our path around the sun. Hidden in the soft glare of dawn and dusk, these companions are called Trojan asteroids, and they gather near the stable Earth-Sun Lagrange regions known as L4 and L5, about 60 degrees ahead of and behind Earth in its orbit. Earth's first confirmed Trojan asteroid, 2010 TK7, was announced in 2010, and it follows a looping, tadpole-like motion around the L4 region rather than sitting perfectly still. Only a small number of Earth Trojans have been confirmed so far, including 2020 XL5, and research describes them as transient, stable for thousands of years, not necessarily for the age of the solar system. They're difficult to discover because, from Earth, these L4/L5 directions sit near the sun in our sky, where sunlight makes faint objects hard to spot with ordinary observing conditions. That's why it's plausible more may exist, quietly sharing our orbital lane, unseen to the naked eye and mostly unnoticed. And in the gentle tone of a bedtime story, it's a comforting thought. Earth is not traveling completely alone. Far ahead and far behind, small stones may be moving with us, keeping their distance, staying steady, while you let your mind do the opposite, slowing down, softening, and beginning to fall asleep. Some comets take millennia to return in this quiet bedtime story. We drift outward beyond the bright planets, to the far edges of the sun's reach, where some comets wait in deep darkness for unimaginably long stretches of time. Some of these comets don't return in years or even centuries, but in thousands, and sometimes far longer. These are often called long-period comets, and they're commonly linked to a distant reservoir known as the Oort cloud, thought to surround the solar system in a vast, roughly spherical shell. The Oort cloud hasn't been directly imaged, but its existence is inferred from the orbits of long-period comets that arrive from many directions, not mainly along the planetary plane. When one of these faraway bodies is nudged by the slow pull of the galaxy or the passing influence of a distant star, it can begin a long fall inward toward the sun. As it approaches the warmer inner solar system, sunlight starts to awaken it. Ices vaporize, a fuzzy coma forms, and a tail stretches out, turning an invisible traveler into something briefly luminous. Some of these comets may only pass through the inner solar system once in recorded human history, simply because their orbital periods are so vast. A few get redirected by planetary gravity into shorter, repeatable paths, but many will fade back into the outer dark for millennia before they ever return, and that can be a comforting thought at bedtime. There are wanderers out there moving on schedules so slow they feel like dreams, appearing, glowing softly for a moment, and then disappearing again into silence, while you let this calming narration carry you toward deep sleep. Solar wind sculpts the Earth's magnetosphere in this relaxing nighttime story. We stay close to Earth and notice an invisible, constant influence. The solar wind presses against Earth's magnetic bubble, shaping it like a steady breeze shaping a sail. I don't have access to live verification tools in this moment, so the rewrite keeps your original structure and avoids introducing new hard numbers. The solar wind is a continual stream of charged particles flowing outward from the sun. When it reaches Earth, it meets the magnetosphere, the region dominated by Earth's magnetic field, and the interaction is dynamic, not fixed. On the sun-facing side, that magnetic bubble is compressed, and on the night side it stretches far outward into a long magnetotail, like a quiet ribbon trailing behind a moving boat. Because the solar wind changes, the magnetosphere changes too. During stronger bursts, such as those associated with solar storms, the pressure increases, the boundaries shift, and the whole system becomes more energized. These disturbances can drive geomagnetic storms that affect satellites and radio communication, and in stronger cases, can stress power systems on the ground. Some of the energy also turns into beauty when charged particles are guided along magnetic field lines toward the polar regions and collide with gases high in the atmosphere. They can produce auroras, the northern and southern lights, soft curtains of color that ripple without sound. Even when nothing dramatic happens, Earth's magnetosphere is still doing its quiet work, deflecting much of the solar wind, trapping some particles in radiation belts, and constantly adjusting its shape to match the sun's changing breath. And that's a soothing thought to fall asleep with above the everyday world. A gentle, invisible shield is always flexing and settling, responding calmly to the solar wind, while you let your own body settle too, slower, softer, and ready for deep sleep. The heliopause, the sun's protective bubble in this gentle nighttime story. We drift outward to the very edge of the sun's influence, to a boundary so distant and quiet that it feels like the solar system's last soft exhale. I can't access sources right now, so the rewrite stays true to your original ideas without adding new hard numbers. The heliosphere is a vast region shaped by the solar wind, and the sun's magnetic field, often described as a protective bubble surrounding the planets. Inside it, the sun's charged particles and magnetic influence dominate. Outside it, interstellar space carries more of the high-energy particles we call galactic cosmic rays. Because of that, the heliosphere acts like a kind of filter. It doesn't block everything, but it can reduce how much of that harsher outside radiation reaches the inner solar system. For life on Earth, it's one of the quiet layers of protection that makes space around us feel less hostile than it otherwise would. At the outer edge of this bubble is the heliopause, the place where the outward pressure of the solar wind finally balances with the incoming pressure of the interstellar medium. Past that boundary, the solar wind can no longer hold the line, and the environment becomes truly interstellar. Before reaching the heliopause, the solar wind passes through another important region, the termination shock, where it slows abruptly as it begins to feel resistance from interstellar space. Between that shock and the heliopause lies the heliosheath, a turbulent mixing zone, less like a clean wall, more like a foamy shoreline where two oceans meet. The shape of the heliosphere isn't perfectly round. It's sculpted by the solar system's motion through the galaxy and by changes in solar activity, expanding and contracting over the sun's cycle like a slow, breathing boundary. And for a bedtime story, that's a peaceful image to hold. Beyond the planets, beyond the comets, beyond the familiar names, there is a gentle frontier, an invisible bubble, where the sun's influence fades into the wider Milky Way, and everything becomes quiet enough to sleep. Uranus is the darkest planet. Uranus, is often described as one of the least reflective major planets in visible light, and that dimness is commonly linked to haze and methane absorption in its atmosphere. In simple terms, even though Uranus looks blue-green, its upper atmosphere chemistry can absorb and mute incoming sunlight instead of bouncing it back brightly. A key ingredient is methane, which strongly absorbs red and near-infrared wavelengths, reducing how much light is reflected back to space at certain bands. Research and explanations aimed at the public also point to excess haze on Uranus. As a reason, it appears more muted than Neptune, with the haze affecting how light scatters and escapes. One small wording note for your script, darkest planet, depends on what exact reflectivity measure and wavelength range is being used. Venus spins backward. We ease back toward Venus again in this relaxing nighttime story, where the light is muted by thick clouds, and even time seems to move differently. Venus has a retrograde rotation, meaning it spins in the opposite direction to most planets, so the sun would appear to rise in the west and set in the east. Venus also rotates extremely slowly. One full sidereal rotation takes about 243 Earth days, while its orbit around the sun takes about 225 Earth days, which is why this fact often gets shared, as a day on Venus is longer than its year. Venus's axial tilt is close to 180 degrees, often given around 177 degrees, which is another way to describe how upside down its orientation is compared with most planets. As for why Venus ended up like this, the cause is still debated, but common explanations include early giant impacts and long-term tidal effects involving the Sun and Venus's dense atmosphere. Atmospheric tides that could slow, stall, and even reverse rotation over very long timescales. Venus's atmosphere also superrotates, with upper winds moving around the planet far faster than the surface turns, adding another strange layer to how Venus behaves. Mars has seasons that last twice as long as we continue this gentle nighttime story. We drift to Mars, where the sunlight feels thinner and the year stretches out, unhurried. Mars has 4 familiar seasons: spring, summer, autumn, and winter, because its axis is tilted in a way that's surprisingly similar to Earth's tilt. But Mars takes much longer to travel once around the Sun, about 687 Earth days, so its seasons last longer than ours, often close to about twice as long overall. And unlike Earth, Mars's seasons aren't evenly sized, because Mars has a more elliptical orbit, meaning it speeds up and slows down along its path. This uneven orbit helps create a difference between hemispheres. The southern hemisphere tends to have shorter, more intense summers, while the northern hemisphere's summer is longer and generally milder. Mars also has a seasonal breathing effect, where carbon dioxide can freeze onto the polar caps in winter and return to the atmosphere as gas in warmer seasons, changing atmospheric pressure and influencing winds. Those winds can lift dust, and in certain seasons, Mars can produce massive dust storms, sometimes large enough to spread across much of the planet, turning daylight into a dim, coppery haze. In the quiet tone of a bedtime story, Mars feels like a world where everything familiar happens more slowly, longer seasons, longer waits, softer changes, inviting you to slow your breathing too and gently fall asleep. The moon stabilizes Earth's tilt in this gentle nighttime story. We stay close to home again and notice a quiet kind of protection that doesn't look like a shield at all. The moon helps keep Earth's axial tilt from wandering too wildly, which supports a more stable pattern of seasons over very long spans of time. Earth's tilt does change, but it stays within a relatively narrow range, commonly given as about 22.1 degrees to 24.5 degrees. And that steadiness is linked to the moon's gravitational influence on Earth's rotational axis. Earlier modeling work has suggested that without the moon, Earth's tilt could become far more erratic, potentially ranging from near 0 degrees up to very high values, often cited as up to 85 degrees on geologically short timescales. The basic idea is simple and soothing. The moon adds stability to Earth's spinning top, reducing the chance that gravitational nudges from other planets push Earth's axis into large, chaotic swings. Mars is often mentioned as a contrast case because its tilt is much less stabilized and can vary substantially over time. And for a bedtime story, it's a comforting image, Earth turning steadily through the dark, with the moon nearby like a patient companion, quietly helping the seasons stay familiar, while you let your own thoughts settle into something steady too, and slowly fall asleep. Jupiter deflects dangerous asteroids and comets in this calming nighttime story. We drift out to Jupiter again, the giant whose gravity reaches far, shaping paths and gently rewriting trajectories. Jupiter really does interact strongly with comets and asteroids, sometimes capturing them, sometimes slinging them onto new routes, and sometimes ejecting them from the solar system entirely. A vivid example is Comet Shoemaker, Levy 9, which was torn into fragments and collided with Jupiter in July 1994, leaving dark scars that were observed for months. Events like that show Jupiter can absorb impacts that otherwise would have continued traveling through the inner solar system. But the Jupiter as a pure shield idea is more complicated than it sounds. Modern discussions in planetary emphasize that Jupiter can be both a protector and a disturber. It can remove some threats, yet its gravity can also redirect certain objects toward Earth-crossing orbits, depending on the source population and orbital details. Studies and summaries often frame Jupiter as a kind of dynamical filter, sometimes reducing impact risk for certain long-period comets, while not necessarily reducing, and in some scenarios, even increasing the impact flux from nearer source objects. For this bedtime story's tone, the gentle way to say it is, Jupiter is a powerful guardian-like presence, but not a perfect bodyguard. It shapes the traffic of the solar system in complex ways, catching some wanderers, scattering others, while Earth continues its quiet journey under the same shared sky. Uranus and Neptune remain mysterious in this soothing nighttime story. We drift to the two far ice giants, Uranus and Neptune worlds, that feel close enough to name, yet distant enough to still keep many secrets. Their they're called ice giants because, compared with Jupiter and Saturn, their interiors are thought to contain larger fractions of ices like water, ammonia, and methane in planetary. Ice can mean these compounds in high-pressure forms, not just frozen cubes. A big reason they remain mysterious is simple. Only Voyager 2 has visited them up close, with a flyby of Uranus in 1986 and Neptune in 1989. Since then, almost everything else has come from telescopes and modeling, which can't fully reveal what's happening deep under their clouds. Uranus stands out for its extreme axial tilt, nearly on its side, while Neptune stands out for a more visibly active atmosphere. And both planets have unusual magnetic fields that don't line up neatly with their rotation axes. That odd magnetism is one reason scientists suspect their dynamos may occur in strange, conductive fluid layers rather than in Earth-like iron cores. Because ice giants are common among exoplanets, learning the true nature of Uranus and Neptune would help interpret many distant worlds more accurately. That's why mission planners and researchers continue pushing for dedicated exploration, including concepts like a Uranus orbiter and atmospheric probe, slow journeys, but ones that could finally turn mystery into understanding. Mercury's extreme temperatures. As this gentle nighttime story continues, we drift close to the sun again, to Mercury, a small world where heat and cold take turns in the most dramatic way. Because Mercury has almost no atmosphere to hold warmth in, the surface can swing from about 430 degrees C in daytime down to about minus 180 degrees C at night. Explains this stark contrast as a direct result of Mercury's lack of a heat-trapping atmosphere, allowing intense heating under sunlight and rapid cooling after sunset. That makes Mercury one of the clearest examples of how an airless world can experience extreme surface conditions, quiet, exposed, and always at the mercy of light and shadow. In the soft tone of a bedtime story, it's peaceful to imagine one side of Mercury resting under fierce sunlight, while the other side waits in deep cold, both silent, both still, while you let your own day fade away and fall asleep. Zodiacal light. Sunlight on interplanetary dust. Zodiacal light is a faint, soft glow seen after sunset or before sunrise, caused by sunlight scattering off tiny grains of dust spread through the inner solar system. It appears along the ecliptic, the same general path the sun and planets follow in our sky, often as a gentle triangular column rising from the horizon when the sky is very dark. That dust belongs to what's often called the interplanetary dust cloud, or zodiacal cloud, a broad, pancake-shaped distribution concentrated near the solar system's main plane. Many sources describe the dust as being supplied largely by cometary dust and collisions among asteroids, with the particles slowly drifting inward over time due to the Poynting-Robertson effect, which gradually spirals dust toward the sun. Zodiacal light is easy to miss because it's so faint that moonlight and light pollution can wash it out completely. But when conditions are right, it looks like a quiet beam of false dawn. A reminder in this relaxing nighttime story that the The space between planets is not empty, but softly filled with drifting grains, catching the sun's light. The sun holds over 99% of the solar system's mass. In this relaxing nighttime story, we return to the quiet center of everything, the sun. The sun contains about 99.86% of the solar system's total mass, which is why its gravity so completely dominates the motions of the planets, moons, asteroids, and comets. Because the sun is so massive, the center of mass of the solar system, the barycenter, usually sits close to the sun, though the tug of Jupiter and the other giant planets can shift it around. In simple terms, nearly everything in our solar system is arranged the way it is because the sun is the anchor, holding the whole system together with gravity. Earth's magnetic field flips over time as this soothing nighttime story continues. We stay close to Earth and listen to a slow, hidden rhythm that has been repeating for ages. Earth's magnetic field can flip its polarity, swapping magnetic north and magnetic south. These events are called geomagnetic reversals, and they're known from paleomagnetic records preserved in rocks and seafloor patterns. Notes that reversals are common in Earth's geologic history, with the last full reversal occurring about 780,000 years ago. A reversal doesn't mean the field snaps off like a switch. During the transition, the magnetic field typically weakens and becomes more complicated, and multiple temporary poles can appear before the field settles into its new orientation. Estimates for how long a transition takes vary, but it's usually described on the order of thousands of years rather than days or years. The underlying cause is tied to Earth's geodynamo, moving, electrically conducting liquid iron in Earth's outer core generates the magnetic field, and changes in that flow can sometimes lead to a reversal. Importantly, agencies like the USGS emphasize that while Earth's field strength has declined by about 10% since modern measurements began, that alone does not mean a reversal is imminent. And in the calm tone of a bedtime story, that becomes reassuring. Earth's magnetism isn't fragile, it's alive, shifting slowly, changing shape over deep time. While you rest safely through one small, quiet night, Europa has an ocean beneath its ice. In this relaxing nighttime story, we drift back to Jupiter's realm, where Europa glides through the dark like a smooth, pale stone, quiet on the outside, but possibly alive with motion underneath. Many scientists consider Europa one of the strongest candidates in the solar system for a hidden ocean, because multiple lines of evidence point to liquid water beneath its icy shell. Europa's surface is coated in water ice, marked by long cracks, ridges, and broken-looking plates that suggest the outer shell has shifted and been renewed over time. That kind of fractured, mobile ice is commonly interpreted as a sign that something softer, like slush or liquid, helps the crust move. The leading explanation for how an ocean could stay liquid so far from the sun is tidal heating. Europa's orbit around Jupiter is slightly non-circular, so Jupiter's gravity flexes the moon as it travels. That repeated stretching and relaxing creates internal friction, gently warming Europa from within and helping prevent its water layer from freezing solid. Another important clue comes from magnetic measurements. Europa appears to produce an induced magnetic signal as it moves through Jupiter's powerful magnetic environment. The simplest way to explain that effect is a global layer that conducts electricity, well, such as salty liquid water beneath the ice. There have also been observations that suggest possible plumes or water vapor above Europa, which, if confirmed, could offer a rare chance to sample material from below without drilling. Future missions are designed to investigate this more carefully by flying past Europa many times, mapping the ice, measuring chemistry, and searching for signs of active exchange between the surface and the ocean. And in the calm language of a bedtime story, Europa becomes a comforting mystery. A frozen moon holding a dark ocean in its depths, warmed by gravity, moving slowly beneath ice, while you let your thoughts slow down too and drift toward deep sleep. Saturn's rings may disappear in this gentle nighttime story. We drift back to Saturn, where its rings look eternal, even though, on a cosmic clock, they may be temporary. Saturn's rings are made mostly of countless ice-rich particles, with some dust and rocky material mixed in, spread into a wide, bright disk around the planet. Despite how massive they look, the rings are extremely thin compared to their width, and they behave more like a drifting swarm than a solid band. Their particles are constantly tugged and shaped by Saturn's gravity and by interactions that create gaps and structure within the ring system. Over long periods, Saturn can also lose ring material through ring rain, where tiny ring particles are drawn inward and end up in Saturn's upper atmosphere. Based on depletion rate estimates, some sources suggest the rings could be greatly diminished or effectively gone on the order of hundreds of millions of years, often cited around 300 million years, depending on assumptions. Some research also argues the rings may be relatively young compared to Saturn itself, which would make our era a special window, one where the rings are still thick, bright, and easy to see. In the calm tone of a bedtime story, it's a peaceful thought. Even the most beautiful structures in the solar system can be part of a slow, natural cycle, appearing, shining for a while, and then quietly fading back into time. Sunlight takes 8 minutes to reach Earth as this gentle nighttime story continues. We pause with one of the softest, strangest truths in astronomy. Sunlight does not arrive instantly at the average Earth-Sun distance, about 1 astronomical unit. Light takes roughly 8 minutes and 20 seconds to reach Earth. So we always see the sun as it was a little over 8 minutes ago. That delay applies to all electromagnetic radiation traveling at light speed, not just visible sunlight. So the first of a solar flare, for example, reaches us in the same calm, predictable time lag. If the sun could somehow switch off in an instant, the sky wouldn't change immediately. Earth would continue in normal daylight until those last photons finished crossing space. In the quiet tone of a bedtime story, it's a peaceful thought. Every warm ray on your skin began its final journey minutes ago, crossing the space between worlds, arriving gently, right on time. As you fall asleep, the sun's core is the hottest place in the solar system In this calming nighttime story, we return to the deepest, brightest furnace we know, the sun's core, which is widely described as the hottest place in the solar system. I can't pull fresh sources right now, but the rewrite keeps your same core facts and structure without adding new or uncertain details. At the center of the sun, temperatures are often given as around 15 million degrees C. This is where nuclear fusion happens, hydrogen nuclei joining to form helium and releasing energy that eventually becomes the sunlight that warms Earth. Even though sunlight only needs about 8 minutes to cross the space from the sun to Earth, the energy's journey inside the sun is far slower. Photons born in the core bounce, scatter, and trade energy again and again through dense solar layers, taking an incredibly long time to reach the surface before they finally stream out into space. Above the core, the sun's layers cool step by step through the radiative zone, then the convective zone, and finally the visible surface that is much cooler than the core. Yet compared to any planet's surface, the sun's interior remains in a class of its own. So, in the soft tone of a bedtime story, it's enough to picture it simply: a quiet, steady heart of heat at the center of our solar system, powering everything while you let your own body cool and rest and drift into deep sleep. The heliosphere forms a giant plasma bubble. The heliosphere is a vast, bubble-like region filled with solar wind plasma and shaped by the sun's magnetic field. And its outer edge is marked by the heliopause, the boundary where the outward push of the solar wind balances the pressure of interstellar space. Voyager 1 and Voyager 2 are widely reported to have crossed into interstellar space after passing this boundary, providing in situ measurements that helped confirm the heliopause as a real physical transition zone. Inside this bubble, the solar wind flows outward until it slows at the termination shock and then passes through the turbulent heliosheath before reaching the heliopause itself. Rather than being a perfect sphere, the heliosphere is described as being distorted by the solar system's motion through the local interstellar medium, often modeled as a rounded nose with a stretched tail. One of the heliosphere's most soothing roles, especially for a nighttime story, is that it helps reduce the intensity of some incoming galactic cosmic rays compared with what would be experienced outside the heliopause. So far beyond the planets, there is an invisible shoreline, a slow, shifting plasma boundary where the sun's influence thins out and the wider galaxy begins. The solar cycle influences Earth's climate as this quiet nighttime story continues. The sun's mood gently rises and falls in a rhythm called the solar cycle, and Earth feels some of those changes, mostly in the space environment and upper atmosphere, and only subtly in surface climate. The solar cycle is often described as an 11-year pattern in which the sun shifts between calmer periods, solar minimum, and more active periods, solar maximum, with changes in sunspots, flares, and ultraviolet output during higher activity. Parts of the sun's energy output and magnetic behavior change, which can influence Earth's upper atmosphere and the conditions that drive space weather. That space weather connection is the clearest and most immediate. Solar storms can disturb Earth's magnetosphere and ionosphere, affecting satellites, radio communication, and power grid stability. These are not weather in the everyday sense, but they are real, measurable changes in the near-Earth environment. When it comes to climate at Earth's surface, the picture is gentler and more complicated. Scientists generally treat solar cycle effects on global temperature as relatively small compared with the warming influence of greenhouse gases. Even though solar variability can add natural ups and downs that climate models still need to account for. Longer-lived changes in solar activity, like extended quiet periods, are sometimes discussed in connection with historical regional cooling episodes, often mentioned alongside the Maunder Minimum and parts of the Little Ice Age. But this relationship is still studied carefully because Earth's climate system has many moving parts, and solar changes interact with oceans, atmosphere, clouds, and chemistry in ways that aren't always straightforward. And for a bedtime story, the feeling is simple. The sun is not a constant lamp, but a living star with gentle cycles, brightening and calming in slow waves, while Earth keeps turning beneath it. And you let your mind settle into darkness, steady and safe, ready for deep sleep. Meteorites carry clues to the solar system's origin. Meteorites are physical pieces of ancient material that can survive entry through Earth's atmosphere, and many are so old and unaltered that they act like time capsules from the solar system's earliest days. Notes that most meteorites found on Earth come from shattered asteroids, and some come from Mars or the Moon, with ages reaching up to about 4.6 billion years. Some of the most primitive meteorites contain chondrules, small, rounded beads formed by rapid melting and cooling in the early solar nebula, which helps scientists reconstruct conditions during planet formation by measuring isotopes, including short-lived radioactive systems. In meteorites, researchers can constrain timelines for early solar system processes and track how materials moved and mixed as planets grew. Meteorites can also contain complex organic compounds, and studying them helps scientists explore how prebiotic chemistry existed in space before Earth was fully formed. Even fragments of differentiated bodies, like iron meteorites that likely come from the cores of broken parent asteroids, offer direct evidence of early melting and layering, teaching us how rocky worlds began to separate into internal structures. Gas giants have rocky cores. Gas giants aren't just gas all the way down. The leading models describe them as layered worlds with denser core material, heavy elements like rock/metal, and depending on the planet, ices buried beneath thick envelopes of hydrogen and helium or other volatiles. For Jupiter and Saturn, the usual picture includes an outer molecular hydrogen region overlying a deep layer of liquid metallic hydrogen, with heavy elements concentrated toward the center, though Jupiter's core may be diffuse or fuzzy, not a clean, solid ball. For Uranus and Neptune, often called ice giants, models still place heavy elements toward the center, but with much more mass in water, ammonia, methane-rich layers, compared with Jupiter and Saturn. Because no probe can directly sample these interiors yet, scientists infer this structure indirectly using gravity field measurements, magnetic field behavior, and interior modeling. So the broad conclusion, dense central heavy element region, is strong, even while the exact core size, state, and sharpness remain active research topics. Moons can become rings inside the Roche limit in this calming nighttime story. We step into a simple but powerful rule of gravity. If a moon drifts too close to its planet, it can be pulled apart and turned into a ring. This boundary is called the Roche limit, the distance where a planet's tidal forces can overwhelm a smaller body's self-gravity. Inside the Roche limit, the near side of the moon feels a stronger pull than the far side, and that stretching can become severe enough to break the moon into countless fragments. Those pieces don't usually fall straight down right away. Many spread out and continue orbiting, forming a thin, wide disk, a ring system. That's why rings often sit close to their planets. The same tides that can destroy a moon also make it difficult for ring particles to reassemble into a single larger moon, while they remain inside that critical zone. Outside the Roche limit, the opposite can happen. Particles can clump together and accrete into moonlets over time. A well-known future example is Mars's moon Phobos, which is slowly spiraling inward and is expected to either break apart into a temporary ring or impact Mars, depending on how the stresses play out as it approaches that tidal boundary. So the next time Saturn's rings come to mind in this bedtime story, they can be imagined as the quiet aftermath of gravity at work, beauty made from a long ago breaking, arranged into a soft, shining band that circles in silence. The moon had active volcanoes billions of years ago in this relaxing nighttime story. We look up at the moon and remember that it wasn't always as quiet as it seems now. The moon shows strong evidence of widespread volcanic activity billions of years ago, and those ancient lava floods created many of the dark plains we see today, called the lunar maria. Those maria are broad, smooth basaltic plains that filled huge impact basins after eruptions poured out runny lava and spread across low ground. Samples brought back by Apollo include volcanic basalts, helping scientists date major phases of lunar volcanism to early lunar history, when the moon still held more internal heat. The simplest reason the moon's volcanoes faded is that the moon is small. Smaller bodies cool faster, and without plate tectonics to continually recycle heat and drive volcanism, activity gradually slowed until large eruptions became rare. There's also growing interest in the idea that the moon may have had small, localized volcanic activity much more recently than once believed, possibly within the last few 100 million years, based on orbital observations and recent sample studies. Pluto's atmosphere is seasonal. Pluto's atmosphere is thin, temporary, and strongly seasonal because it's controlled by surface ices that can sublimate into gas when warmed and then refreeze back onto the ground when Pluto cools. I don't have access to browsing right now, so this rewrite keeps your original structure and avoids adding any new precise figures. Pluto's orbit is highly elliptical, so its distance from the Sun changes a lot over its long year. When Pluto is closer to the Sun, nitrogen ice, with smaller contributions from methane and carbon monoxide, can warm enough to turn directly into gas building a fragile atmosphere above the surface. As Pluto moves farther away again, temperatures fall and much of that gas can condense back down as frost, thinning the atmosphere dramatically. Because Pluto takes centuries to complete one orbit, its seasons last for decades, not months. That slow pace makes the atmosphere feel like it's breathing on a very long timescale, expanding, softening, and then slowly collapsing again. Observations from Earth through stellar occultations and the New Horizons flyby showed that Pluto can maintain a measurable atmosphere even as it travels away from the Sun, suggesting the timing of collapse isn't instant and can lag behind Pluto's changing distance. Haze layers can also form, created when sunlight breaks apart methane and builds tiny particles that hang in the thin air like a faint, golden fog. In the quiet tone of a bedtime story, Pluto becomes a distant world that doesn't just sit frozen and still. It gently changes with the light, gaining an atmosphere, losing it, and repeating that cycle over a slow, patient orbit at the edge of our solar system. Sun-grazing comets vaporize in the sun in this gentle nighttime story. We drift closer to the sun than most objects ever dare to go, and meet the sun-grazing comets, small, ancient travelers that pass so near the solar furnace that many are simply erased. Sun-grazers follow orbits that bring them extremely close to the sun. As they fall inward, sunlight cooks their surface ice into gas, building a bright coma and tail for a brief, dramatic moment, like a candle flare right before it goes out. Under that intense heat, the comet's ices and fragile material can rapidly vaporize, and near the sun, the material can become ionized, blending into the hot, charged environment around the star. Gravity matters too. Near the sun, tidal forces can stretch a comet, especially if it's already fractured or loosely held together. Some sun-grazers break into pieces before they vanish, and the fragments can each glow briefly, then fade one by one. Space-based solar observatories have caught many of these events. Tiny comets appearing as bright specks in coronagraph images, diving inward, and then disappearing as they disintegrate. This has revealed that sun-grazers are common, especially in well-known families of related comets that likely formed when a much larger comet broke apart long ago. Not every sun-grazer dies the same way. A few rare ones survive a close pass, at least temporarily, before breaking up later, weakened by heat and stress. But most are short-lived visitors. They brighten, unravel, and become part of the sun's surrounding environment. And for a calming bedtime story, the image can stay simple. A small, icy body falling toward a brilliant star, glowing softly for a moment, then dissolving into light and silence as you drift toward deep sleep. Jupiter's equator spins faster than its poles. Jupiter shows differential rotation. Because it's a fluid world with no solid surface, its atmosphere doesn't rotate as one rigid body, and the equatorial regions complete a turn a few minutes faster than higher latitudes. One common way this is described is with two different systems used to track Jupiter's rotation. Near the equator, System I, the rotation, is about 9 hours 50 minutes, while at higher latitudes, System II, it's closer to 9 hours 55 minutes. That small difference, only a few minutes, matters because it helps power the strong jet streams that create Jupiter's bright bands and darker belts. And it supports long-lived storms by adding shear between neighboring atmospheric flows. Jupiter's rapid spin also contributes to its visibly squashed shape, an equatorial bulge that's easy to notice in images. Another gentle reminder that this planet is always moving, always flowing, even as you listen to a calming narration and let yourself fall asleep. Earth occasionally captures temporary mini-moons. Earth usually has one familiar moon, but it can also temporarily capture small asteroids into short-lived orbits, creating mini-moons, also called temporarily captured orbiters. No citation available. One well-documented example is asteroid 2006 R120, which was temporarily bound to Earth for about a year in 2006-2007 before it escaped back into a solar orbit. No citation available. Another widely cited case is 2020 CD3, which spent time as a temporary natural satellite before leaving Earth's vicinity. No citation available. These objects are typically very small and faint, which is why they're hard to spot and often only recognized after careful tracking. No citation available. Their orbits are also unstable because Earth, the Moon, and the Sun are all tugging on them at once, so the capture usually ends within months or a few years. No citation available. If you paste the next part, this can be rewritten in the same calm style, while also tightening any numbers and examples you want to keep. Mercury shows aurora-like emissions. Despite no atmosphere, Mercury can produce aurora-like emissions even though it has no true thick atmosphere, because its global magnetic field can funnel solar wind electrons down toward the planet. When those charged particles slam into Mercury's surface, rather than atmospheric gases, they generate high-energy glow, especially X-rays. So the effect is auroral in mechanism, but not a visible sky curtain like Earth's. Recent analyses using BP Colombo flyby data describe electrons being accelerated within Mercury's magnetosphere and then precipitating onto the surface, which is consistent with the idea that Mercury's auroras touch the ground. This helps explain why Mercury's auroral signature is detected by instruments as X-ray emission patterns instead of being seen as colorful lights in an atmosphere. This same particle bombardment is also part of how Mercury maintains its extremely thin exosphere. Solar wind and micrometeoroid impacts can eject atoms from the surface, creating a tenuous cloud of particles around the planet. And now, if your eyes feel heavy, you can let them stay closed. Let the muscles in your face relax. Let your breathing slow down, one gentle breath at a time. You can return to this sleep story, this calming narration on Sleepy Story Facts, any night you want something peaceful to listen to while you fall asleep. For now, there's nothing else you need to do. Just drift and rest and sink gently into deep sleep. As the words grow quieter and the space between them grows wide and everything fades into stillness,